In this class, I am going to talk about the hybridization in square planar molecules. Hybridization in square planar molecules. Hybridization in square planar molecules. Okay. So you already know the square planar molecules. You are very familiar with the transition metal complexes having square planar geometry, and also you know other molecules formed by the main group elements also having this geometry. So I am going to talk about the hybridization in this type of square planar molecules, and I am going to assign the hybridization in these molecules based on their symmetry. Okay, for example, you know NiCN 4 times 2 minus. Okay, you already know this complex. And you know that the hybridization present in this complex is DsP2 hybridization. You know all this already. That is why it is having the square planar geometry. This type of things we have already learned. Okay, and here I am going to give you a quantitative description of why this type of complexes are adopting the DsP2 hybridization, or which are the d orbitals and p orbitals involved in this type of hybridization. Okay, these are the things that we are going to check group theoretically, or by means of examining the symmetry of the molecule. And for that we have to assign the point group of this molecule, of these square planar molecules. You know that in the square planar molecules, we have a central atom in the midpoint of a square. Okay, let me draw this here. The midpoint of the square, we have a central atom. Okay, and the central atom is this one. This is the central atom. Okay, somewhere here. Okay, and there are 4 bonds to the corners of this square, where in each corner another atom is occupied, another type of atom is occupied. For example, I can draw 4 bonds to these corners. Okay, you can see like this. So the central atom will be occupying this position. Sorry, let me complete. Okay, so central atom will be occupying this position, the midpoint. Okay, here the central atom will be there. Okay, this is the midpoint, and these corners of the square will be occupied by some other atoms or groups. Okay, okay, so here will be one atom, another atom will be there, and another atom will be here, and another atom will be here. Okay, so this is how the square planar molecule will look like. And you know that this is a planar molecule, and the molecular plane is the plane of the board itself. Okay, and now I am going to list the symmetry elements present in this square planar molecule. You already know some of the symmetry elements present here, and but we have to have a careful understanding of the geometry of this type of molecules to understand which are the symmetry elements present there. I am going to list these symmetry elements here. Okay, and then I will tell you to which point group it will belong to. Okay, so first of all, we can understand that there is an axis, there is a principal axis passing through the central atom, and that principal axis is perpendicular to the plane of the board itself. Okay, it means that if you are just fixing a nail here, okay, and that will be an axis, a C4 axis. അപ്പോൾ നിങ്ങളിവിടെ ഒരു ആണി വല്ല അടിച്ച് തറയ്ക്കുകയാണെന്നുണ്ടെങ്കിൽ ആ ആണി എന്ന് പറയുന്നത് ഒരു C4 ആക്സിസ് ആയിരിക്കും അല്ലേ. So at every 90-degree rotation, it will give identical orientations. So the C4 axis is here, and since I have drawn this molecule in the plane of the board itself, it is actually impossible for me to draw the C4 axis because the C4 axis will have its projection as a point here. Okay, if we are looking through the C4 axis, okay, looking from the top of the molecule, the C4 axis will be here. And So let me draw it here. Let me write it here. The C4 axis will be passing through this point. And so let me draw it here. Let me write it here. The symmetry elements. Okay. Obviously we have E. Okay. Identity operation is there. Then we have a C4 there. Then we have a C4 square. C4 square is not an element, but it is a unique operation. C4 operation means 90-degree rotation. C4 square means you perform C4 two times, and then we have C4 three times. Okay. And here we have to eliminate the non-redundant symmetry operation, because here you are performing C4 two times, that is equal to a C2 operation. Therefore, this one should be discarded and this should be considered as a C2 operation. It should be considered as a C2 operation, because 2 times 90-degree rotation means that you are rotating the molecule by 180 degree. Okay, and if you are rotating the molecule by 180 degree about this axis itself, means you consider that the C4 axis is the C2 axis, and then you are rotating the molecule by 180 degree, then it is equal to performing C4 two times. Therefore, C4 square should be considered as a C2 operation. Okay, and the next one is after C4, you can consider now the C2 axis. Okay, C4 is the principal axis. Now there are some subsidiary axes perpendicular to this Z4 axis, and these axes. See, one of the type of C2 axis is here. This is one type of C2 axis. Okay, and another one is here. Another one of the same kind. Sorry, my lines are not in the proper line. My dots are not in the proper line. Okay. So this is another C2, and there is other type of C2 axis that is through here. Okay, is through here, and another one of the same kind is through here. Okay, so there are two types of C2. There are totally 4 C2 axes, and out of the 4 C2 axes, there are two types of C2 axes. Let me call this one as a C2 prime and this one as a C2 double prime. Okay, so there are two C2 primes. This is also a C2 prime, and this is also a C2 double prime. Okay. So these are the other symmetry operations. Let me write that also here. So we have a C4 cube, then 2 C2 dash or C2 prime, 2 C2 prime, then 2 C2 double prime. Okay. Then the next one is inversion center. See, this center, the center of the square is an inversion center. So this is an inversion center. So I have this inversion center also here, I. Then I have a S4. Why I have S4? This C4 axis, that is the axis passing through this point, that is perpendicular to the molecular plane, that is C4 axis. That C4 axis is an S4 axis also. Or in other words, we can say C4 axis and the S4 axis coincides. S4 means you are rotating it by 90 degree and making a reflection about the axis of rotation. So if you are rotating this molecule to 90 degree, then this corner will reach here. Okay, so each corner will shift to the adjacent corner position. Okay, that is a 90 degree rotation. After that, you are making a reflection about the plane perpendicular to the rotation, that is the molecular plane itself. So after this 90 degree rotation, if you are making a reflection about the molecular plane, then you will get an identical operation, identical structure or identical orientation. So this orientation is identical to the origin orientation. So this is an S4 axis. C4 axis itself is an S4 axis. So let me write the S4 there. So S4 is another operation present there. Then I can write the S4 square. Okay. Then S4 cube. S4 cube means S4 3 times. But here S4 square you cannot write it as such, because this is also this is not a unique operation, or it is not a non-redundant operation, because S4 square is equal to C2. Okay, this is C2 itself. So we have already listed C2 here. So therefore we don't need to write S4 square again. Okay, and then we have a S4 cube. Then we have which one? After S4 we have sigma h. Okay, this is a sigma h plane. So the molecular plane is a sigma h plane. Okay, so we have sigma h. After that we have sigma v. Okay, sigma v planes means vertical planes, means plane which contains the principal axis, that is a vertical plane. So there are two kinds of sigma v planes. There are actually 4 sigma b planes in total, and they belong to two types. Okay, one of the type of sigma b planes are the planes which contains the bonds. See, if it is containing these two bonds, that is a sigma v plane, or sigma v plane containing C2 prime axis. Okay, C2 prime axis involve in a sigma v plane. അതൊരു ടൈപ്പാണ്. അങ്ങനെയുള്ള രണ്ട് സിഗ്മ ബി പ്ലെയിൻ ഉണ്ട്. ഇതിലേക്കൂടെ ഉണ്ട് അങ്ങനെ ഒരു സിഗ്മ ബി പ്ലെയിൻ. സോ there are two sigma b planes. This represents a sigma b plane, and this also represents a sigma b plane. Okay, so the vertical plane containing the C2 dash axis, or vertical plane containing the bonds. Okay, so that is the sigma b planes. How many sigma b's are there? Two sigma b's are there. And now there are another kind of vertical plane, that is the vertical plane containing C2 double prime. Okay, so those vertical planes are actually bisecting the bond angle present in the square planar complex. Okay, so ഇങ്ങനെ പോകുന്ന ആ vertical plane ആണ് ഇത് സിഗ്മ വി അതൊരു വെർട്ടിക്കൽ പ്ലെയിൻ ആണ്. പക്ഷെ അത് ബോണ്ടുകളെ ബൈസെക്ട് ചെയ്യുന്നതുകൊണ്ട് അതിനെ ആ വെർട്ടിക്കൽ പ്ലെയിനെ നമുക്ക് ഡൈഹീഡ്രൽ പ്ലെയിൻ എന്ന് വിളിക്കാം. ഓക്കെ, ഡൈഹീഡ്രൽ പ്ലെയിൻ. ഓക്കെ, സോ സിഗ്മ ഡി എന്ന് വിളിക്കാം അതിനെ. ഓക്കെ, സോ that is sigma v and sigma d. How many sigma d's are there? Two sigma d's are there. ഇങ്ങനെ ഒരു sigma d ഉണ്ട്, ഇങ്ങനെ ഒരു sigma d. Two sigma d's are there. Okay, so these are the symmetry elements and corresponding symmetry operations. After that, now you can consider actually S2 also. Actually this C2 double prime, this is actually an S2 also. Okay, and this one, that is C2 prime, actually acts as an S2. Okay, because you can, S2 means you rotate this by 90 degree. When you rotate this by 180 degree, so after 190 degree rotation, this corner will reach here. Then there is a reflection about a plane perpendicular to this one. So this corner will reach here. So that is also a symmetry operation. But the problem is that you cannot consider this S2. Okay, either of this S2, because S2 will be equal to inversion. Okay, S2 will be equal to inversion. You suppose that this is after you consider that this is S2 axis. You rotate this molecule by 90 degree, then this corner will reach here first, then after the reflection it will reach here. Okay, so this corner which was originally here has reached now here. So that is equivalent to inversion. So we don't need to list the S2 operations. Okay, so these are the non-redundant operations present in the molecule, in this type of molecule. So these operations show that this belongs to which point group? There is a principal axis C4, and there are four C2 axis or subsidiary C2 axis perpendicular to the C4. Okay, two Z2 primes and two Z2 double primes. So it is D4. Okay, C4 plus 4 C2 is equal to D4. Now there is a horizontal plane, so it is a D4H. So this type of molecule belong to D4H point group. So let me list the non-redundant symmetry operations present in the D4H. Okay, these are E. Okay, then we have C4 and C4 cube. Together we can write 2C4, because in character table we will write like this. These two will belong to the same class, that's why we write like this, 2C4. Then we have C2. Okay, C2, and then we have a 2C2 dash, then we have a 2C2 double dash or double prime, then we have a inversion center I, Then we have 2s4. S4 means 2s4 means s4 and s4 cube. That is 2s4. Okay. Then we have sigma h. Then we have 2 sigma v, 2 sigma v, and then we have a 2 sigma d. Okay. These are the elements, or these are the elements of the point group. Okay. And how many elements are there in the point group? Totally there are 16. You can count all these together, then it is equal to 16. Therefore, order of the group is equal to 16. Order H is equal to 16. Now I am going to give you the character table of this point group. Character table of this point group. Okay, here is the character table of the D4H point group. Character table of D4H point group. And from this character table, I am going to assign the total character belonging to a reducible representation corresponding to the orbitals, the hybrid orbitals present in this molecule. Seems very complicated. No need to worry. We have a square planar complex here, right? Square planar complex. And let me take the square planar complex to downside so that I can show you all the time. Okay. So here is the square planar complex. Okay. I will paste it down because we can watch it every time. So here is our square planar molecule. Okay. And what I am going to do is I am going to construct or I am going to consider 4 bond vectors in this one. 4 bond vectors. Bond vectors means the vector passing through the bonds. Okay. So I am going to consider the bond vectors here. Okay. This is one bond vector. This is one bond vector. This is another bond vector. Which one? This one. Okay. This is another bond vector. And here is another bond vector, and here is another bond vector. Bond vector means these are passing through the bonds. Okay, so these are vectors. So here is the arrow of the arrowhead of the vectors. The vectors are in this direction. Okay, why I have drawn these bond vectors? Because these bond vectors are the same direction of the hybrid orbitals. And this molecule has a square planar geometry because the hybrid orbitals are oriented to the 4 corners of a square. Okay, the hybrid orbitals are oriented to the 4 corners of a square. So any vector passing from the central atom to the corner of the square will show you the direction of the hybrid orbital. Okay, now I am going to assign the total character corresponding to these bond vectors. Okay, and that will be the total character corresponding to the hybrid orbital also. So the total character can be now assigned depending upon or checking how many of these vectors are retaining their position during each operation. Okay, so I am going to write the total character here. The total character. So the total character belonging to each operation. So the operations are already here. Okay, let me take these operations to the downside. Okay, so these are the non-redundant operations. I will take this here and I will write the total character corresponding to all of these one. Okay, the total character corresponding to this. So the total character corresponding to these ones, the total character. Gamma t. Let me write gamma t. Gamma t is the total character. I am going to list the total characters here. Okay. And corresponding to E, the total character is equal to 4 because during the E operation or identity operation, none of the vectors will change their position. All the vectors will retain their position. All the 4 vectors will retain their position. Therefore, the total character is equal to 4. And what about C4? C4 is the rotation about the principal axis. This principal axis. The axis is perpendicular to the plane of the bond. So during the C4 rotation, none of the bonds will retain their position. All the bonds will change their position, right? Therefore, the total character is equal to 0. And what about C2? C2 is a 180-degree rotation. Same is the case, right? All the bonds will change their position. So that is also equal to 0. What about C2 dash? C2 dash. C2 dash is, you should be very careful here. C2 dash is the rotation through this axis, and that axis actually contains two of the bond vectors or two of the hybrid orbitals. Therefore, these two vectors will retain their position. Okay, the vectors which are already in a symmetry element will retain their position. Other vectors will change their position. So two vectors will retain their position during C2 dash. Therefore, the total character is 2. But what about C2 double dash? C2 double dash does not contain any of the vectors. Therefore, all the vectors will change their position. So, the total character is equal to 0. What about inversion? During the inversion means it is a point. All the vectors are outside this point, means the inversion center, that symmetry element does not contain any of the vectors. Therefore, we can write that the total character is 0. What about S4? S4 axis coincides with the C4 axis itself, and that's a 90-degree rotation. Therefore, all the vectors will change their position. Therefore, the total character is 0. What about sigma h? Sigma h is the molecular plane itself. All the bonds are in the molecular plane. Therefore, during the sigma h, none of the bonds will change their position. All the bonds will maintain their position. Therefore, sigma h, total character corresponding to sigma h is equal to 4. And what about the sigma v? Sigma v means this one. Which one? This vertical plane, right? The plane which is perpendicular to the plane of the board, and at the same time it contains two of these vectors. So they will not change these two vectors will not change the position. Therefore, during sigma v, the total character is equal to 2. Okay. What about sigma d? Sigma is the d is the dihedral plane that is bisecting the bond angle between any two of bonds, right? So that vertical plane or that mirror plane does not contain any of the sigma any of the vectors. Therefore, the total character corresponding to that is equal to 0. If you want to specify these vectors, you can call this as R1, R2, R3, and R4. Okay. So these are the total characters corresponding to different operations. Now what I am going to do is, I am going to apply the reduction formula here. And this total character is a character of a reducible representation. That reducible representation corresponds to the hybrid orbitals, right? And I have to see which are the irreducible representations contributing to this reducible representation. And in order to find that, we have to apply the reduction formula. And reduction formula will tell you how many times each irreducible representation will appear in a reducible representation corresponding to a given total character set. Okay. So I am going to write the reduction formula here. I have given a detailed lecture of the reduction formula. If you are new to this lecture, I recommend you to go back to that lecture on reduction formula, have an understanding of that, and come back and watch this one. And the reduction formula says that Ni, that is the number of times the ith irreducible representation will appear, that is equal to 1 divided by h into sigma, then gr chi ir chi r. Okay, chi r, where h is the order of the group. In our case, it is already 16 in our case, and gr is the number of elements in a class represented by the operation r. Okay, here you can see that C4, this is an operation, C4 is an operation, and 2 times the number of elements are appearing here. Means there are two C4 operations, C4 and C4 cube. So the number of elements in this class is equal to 2. So if you are considering R as C4, then GR is equal to 2. Okay, and chi R is the character corresponding to the operation R in the ith irreducible representation. For example, if you are taking the first irreducible representation A1G, then chi ir corresponding to C4 is equal to 1. Okay, and chi r is the character of the total character set, the character corresponding to R in the total character set. So in the total character set, it is 0 corresponding to C4. So chi r is equal to 0 in this case. So we have to do this for every operation, and after doing this for every operation we have to sum up those things, and then we will get a sigma r gr chi r chi r, and then we have to divide that quantity with the order of the group. That will give you the number of times an irreducible representation will appear. The irreducible representation that you are considering to make this calculation, that will appear in the total character. Okay, so that will appear in the reducible representation corresponding to the total character. So I am going to do this calculation. So I am going to calculate the first one, n_a_1g. Okay, n_a_1g. So let me take n_a_1g here. This is n_a_1g, and I am going to put it down so that we can see this all the time. This one is n_a_1g, n_a_1g. Okay, let me copy this and put it down. a_1g. So this is a_1g, a_1g. So I am going to find out the total character corresponding to this a_1g. Total character corresponding to this a_1g. Okay. And what I have to do, I have to apply the reduction formula. In the reduction formula, we have 1 divided by h, and in our case, h is equal to 16. Order of the group is equal to 16. So I can write n_a_1g is equal to n_a_1g is equal to 1 divided by 16 into. Now we have to find out this sigma gr chi r chi r. Okay, so we have to do this one for every r. So let me take e. Then e, in the case of e, it is gr is equal to 1. So I can write 1 into chi r is equal to 1. The first character is equal to 1 into chi r in this case is equal to 4. So 1 into 1 into 4, that is equal to 4, plus, okay, the next one I can neglect because the next one in chi r in the case, next case is 0, and the other one is also 0. So these two I can neglect. I don't need to waste my time calculating all this. So I have to calculate this one, okay, this one. Then I have to calculate this one, okay, and then I have to calculate this one, this one, okay. All other things will give 0. Okay, so we don't need to waste our time to find those things. So let me directly go to C2 dash. So C2 dash, in the case of C2 dash, 2 into 1, that is equal to 4, plus. Then I go directly to sigma h. 4 into 1 into 4 into 1. Okay, so that is equal to 4, plus. Then 2, that is gr. 2 into 1, that is equal to 4. Okay, that is equal to 4 plus 4 plus 4 plus 4 by 16, that is equal to 16 by 16, that is equal to 1. Okay, so now you can do the similar calculation for other irreducible representations also. But one thing you have to remember here, you don't need to calculate for all these irreducible representations. How many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 irreducible representations are there. You don't need to write all these for 10 irreducible representations. You pick only those which belong to some atomic orbital. Okay. For example, you can see here that z square, that belongs to dz square orbital. That is why we picked a_1g. Okay. And the next one corresponding to some atomic orbital is x square minus y square. This corresponds to a d orbital. So we can pick this one, b1g. Okay. Then after that we can pick xy because that also belongs to a d orbital. So b2g. Then after that this one xz yz, that also belongs to d orbital. So we will pick eg for the calculation, and we don't need to go for a1u because that doesn't belong to any of the atomic orbitals. Then after that we will go for Z, because this belongs to pz orbital. So we will pick A2U. Okay, after that we will pick last one, that is EU. Okay, we will pick EU because that belongs to Px and Py. So we need to pick only 1, 2, 3, 4, 5, 6. 6 of these irreducible representations for calculations. Okay, don't waste time behind all other irreducible representations. And now I am going to calculate the next one, that is NB1G. NB1G. Okay, NB1G. So NB1G is equal to, you can calculate in the same way, that is equal to 1 divided by 16 into 4 plus 4 plus 4 plus 4. Okay, that is equal to 16 by 16, that is equal to 1. So NB1G is equal to 1. And NB2G, next one is NB2G. Okay, you need to pick only NB2G. NB2G. After that EG, then A2U, and then EU. Okay, so I will write for these things also. So now you can calculate NB2G, and NB2G is equal to 1 divided by 16 into 4, then minus 4, then plus 4, then minus 4. That is equal to 0. Okay, and NEG is equal to 1 divided by 16 into then 8, because in the case of EG you can see that the character belonging to E is equal to 2. Okay, this is a two-dimensional representation, so that is why it is 8 here. So 8, then all other things will become 0, and then you will have another minus 8, that is coming from here. Okay, minus 8. You can look here, the EG, say there is also a minus 2 here. See, minus 2 here. So so one a 2 here, and then where is it? Yeah, 2, 0, minus 2, 2, then 2 minus 2. Okay, that minus 2, then 0, 0. Okay, so from these ones you will get a minus 8, and then you have, because belonging to sigma 8 you have 4 as the total character, so minus 2 into 4 is equal to minus 8. That is why minus 8. So 8 minus 8, that is equal to 0. And from here, next one is A2U, that is N A2U, that is equal to 1 divided by 16 into 4 minus 4 plus 4, that is equal to 0. Okay, and NEU, you do it yourself from the character table. 1 divided by 16 into 8 plus 8, that is equal to 1. Okay, so this is how we can apply the reduction formula for the character table. Okay, and I have shown in detail for one of these reducible representation. You can follow the same method for the other irreducible representations also. So from the reduction formula, now you understand that the total character, the reducible representation corresponding to the total character, gamma t, is equal to A1G plus B1G plus EU. Okay, so this is your result. Now you can check whether your result is correct or not just by summing up the dimensions of these irreducible representations. For example, the dimension of A1 is equal to, dimension is equal, this is one dimensional representation, this is also one dimensional representation, this is two dimensional representation. So 1 plus 1 plus 2, that is equal to 4, and this 4 should be equal to the number of hybrid orbitals that you are expecting. Okay, so in the case of square planar complex, you are expecting 4 hybrid orbitals, so this should be equal to 4. The sum of the dimensions must be equal to 4. Okay, then only your calculation will be correct. And then Now we are going to assign which are these atomic orbitals. So we have A1G here, A1G, A1G, then we have a B1G, then we have EU. Okay, so these are contributing to the hybrid orbitals. So which are the hybrid orbitals corresponding to A1G? That is a totally symmetric irreducible representation, A1G, the first one. And you can see that Z square belongs to that, Z square. So dZ square belongs to this one. In addition to that, there is another orbital, that is S orbital. S orbital is not mentioned in the character table because it is not needed to mention that, not needed to mention S orbital here, because S orbital is a totally symmetric orbital. It is spherical in shape. So always a totally symmetric irreducible representation will belong to the S orbital also. Okay, so actually A1G belong to S orbital and dZ square orbital. Okay, S orbital and dZ square orbital. So let me write it here. A1G is S orbital or dZ square orbital. And what about B1G? B1G. And B1G is belonging to dx square minus y square, right? B1G belong to dx square minus y square. So let me write it there. So there is only one orbital for B1G, that is dx square minus y square. Dx square minus y square. And what about EU? There should be two orbitals corresponding to EU, because that is a two-dimensional representation, and there will be two degenerate orbitals corresponding to EU. And we will check what are these degenerate orbitals corresponding to EU. X and Y, that is Px and Py. It is written inside the bracket. It means that they are degenerate set. Okay, Px and Py. Okay, Px and Py. Px, then Py. Okay, these are the orbitals. So these are the orbital sets available for the hybridization. So it is compulsory that one s orbital should be there. That is our result, right? One A1G plus one B1G plus one EU. So one of the s orbitals, either it is S or dz square. Okay, one of the A1G orbital, whether it is S or dz square. And one of the B1G, so there is only one B1G type, that is dx square minus y square. And one EU, and in the EU, you can see Px and Py, they are degenerate set, they transforms together. So Px and Py should be always considered together. So dx square minus y square, Px, Py, these are compulsory. Okay, these are compulsory. And the option is only here. Either it is S or it is dz square. So your combinations are the possibilities. The first possibility is that S orbital plus dx square minus y square plus Px plus Py. Okay, this is one combination. And the next combination is, in place of S you have dz square, then other orbitals are compulsory, that is dx square minus y square plus Px plus Py. These are the two combinations. Okay, so we can check what are the possible combinations. This is set by group theory. Group theory will tell you what are the possible combinations of atomic orbitals giving rise to a given hybrid, giving rise to a particular type of hybrid orbital. Okay, or giving rise to the formation of a particular molecule in a particular point group. That only group theory will tell you. Or group theory will tell you what are the combinations allowed by symmetry. So this is okay by symmetry, means s orbital, one s orbital, then ds square minus y square, then px and py is allowed to combine to form the hybrid orbitals. They are okay by symmetry. And the same way dz square orbital, ds square minus y square, px and py, they are also allowed to be combined by symmetry. Okay, so these are allowed by symmetry, but what is possible should be determined by other factors also. For example, you have to consider the energy of the orbitals. If the orbital has to combine, the orbitals must have almost similar energy, then only they can form the hybrid orbitals. Okay, and also the availability of the orbitals. For example, in particular atom, you are making the you are considering this hybridization for a particular atom, and that atom will have a configuration which is different from another atom that you are considering next, right? So the availability of orbital in each atom will be different. So you have to consider the availability of the orbitals, you have to consider the energy of the orbitals, and all this, then you have to consider the symmetry also. And here we are satisfying only one. Here from group theory, we are going to find out only one criterion, that is symmetry. Okay, if other criteria also are satisfied, then it is possible to form the hybrid orbitals. So we can check what is the possibility in NiCN 4 times 2 minus, that is a non-square planar complex, NiCN 4 times 2 minus, right? So let us check what happens there. NiCN 4 times 2 minus. Okay. So in this complex, nickel is a central atom. Okay, the atomic number of nickel is 28. Therefore, its configuration is, nickel's configuration is 3d8, 4s0, 4s2. Okay, then 4p0 like that. Okay, 4p0. Okay, this is the configuration, electronic configuration of nickel in the zero oxidation state. And in this complex, nickel is in the +2 oxidation state. So we have to consider Ni2 plus. So in Ni2 plus, you have the configuration 3d8, 4s0, okay, 4p0. Okay. So if I am drawing these in the box, means the electronic configuration in the box, then I can write it like this. For example, these are the 3D orbitals. 5 orbitals are there. Okay, 3D orbitals. Then we have the 4s orbital. Then we have the 4p orbital. Okay, 4p orbital. So this is 3D. This is 4s. Then we have 4p orbitals. So let me put the electrons inside the 3D orbital. We have 3d8. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, 8 electrons are there in the 3D. So 3 of the d orbitals will be fully occupied, means 3 of the orbitals are doubly occupied, and but the other 2 orbitals, d orbitals, are singly occupied, and s orbital is vacant, p orbital is also vacant. Okay, so during the molecule formation, okay, then the cyanide ligands will it will force these electrons to pair up, so that during the formation of the bond, then this d orbital configuration will become like this: 1, 2, 3, 4, 5, 6, 7, 8. It will be like this. So it will be paired, and one of the d orbital will be vacant. Then we have 4s, and then we have 4p also. Okay, and now this d orbital and this 4s orbital and 2 of the 4p orbitals can combine by symmetry, because our group theoretical result says that the s orbital, then one d orbital and 2p orbitals can combine to form the hybrid orbitals. So this is the s orbital. So this is s orbital. From here, this is a s orbital, that is actually 4s orbital. Then we have dx square minus y square. That is very important. It is not dxy or dz square or something like that. It is dx square minus y square. Okay, so s orbital will combine with dx square minus y square, and then it has to combine with px and py, not pz. Okay, so we have to consider only symmetry allowed orbitals, px and py. Okay, so these orbitals will combine to give you the hybrid orbitals. So the combination will be like this. Okay, see, these they will combine like this. Sorry. They will combine like this, and 4 of these orbitals will combine. What are these 4 orbitals? Dx square minus y square, then s and px and py, and here the d orbital comes from the third shell, and the s orbital comes from fourth shell, and px and py also come from the fourth shell, 4px and 4py. Okay, so you get a dsp2 hybridization. So this dsp2 hybridization is a symmetry allowed hybridization, as it is evident from this result. This is dsp2 hybridization, right? This is dsp2 hybridization. So in the group theory, from the group theory, we can not only know that it is dsp2 hybridization possible for this molecule, we can also know that which are the d orbitals and which are the p orbitals involved in the hybridization. That is very important, right? You can see here that in this hybridization, the d orbital involved is the x square minus y square. That is in the xy plane, right? And the px orbital and py orbital, these two orbitals are also in the xy plane. So all the orbitals are from the xy plane. All the orbitals having some directional character. They are in the xy plane. S orbital is a spherical orbital. That it doesn't have any directional character. It is a sphere. So all the orbitals having the direction character, they are in the xy plane. Okay, that is very important. So this is forced by the symmetry of the molecule. Okay, so we are getting very important information from the group theory. And here you can see that if s orbital is replaced by dz square, it is possible by symmetry. Okay, s orbital is replaced by dz square, it is possible by symmetry. But whichever is more energetically feasible, that will be formed. But by symmetry wise, this is possible. Okay, so this is corresponding to D2P2 combination, right? D2P2 type of hybridization, but that is going to be very, very rare. And the most common hybridization that we have seen, and which is energetically possible and which is possible by quantum mechanical results also, is the DsP2 hybridization. Okay, but group theory also says that, yeah, in suitable conditions, perhaps this is also possible. D2P2 is also possible. Okay, maybe you can work out on that. And this is what we can understand from the group theory. Okay, and I hope you understood the hybridization in the square planar molecules. And in the last class, we discussed on the hybridization of the tetrahedral molecules. There you saw that the hybridization that we devised was sp3 hybridization. There also we had a central molecule and 4 atoms which are bound to the central atom. Here also we have a not central molecule, central atom. Here also we have a central atom and 4 atoms are bound to the central atom here also. Okay, so even if the coordination number is same, okay, the hybridization is different. There we ended up in sp3 hybridization most probably, or in the case of the transition metals, other hybridizations were also discussed, okay, involving the d orbitals. But here we can see that the hybridizations possible here and there are different. Okay, and this depends upon the symmetry of the molecule. Okay, so I hope you understood this also, and if you have any doubt, please don't hesitate to ask me. Thank you for watching and stay tuned.